Okay, so do we have a decent amount of CH3COO minus to react with H3O plus? And the answer is no. So the fact of the matter is it is going to shift left, but then it's going to go like left clunk, right? Because it can't go left any further because there's not enough stuff there to let it go left. So will it be able to absorb that extra H3O plus and keep the hydronium concentration quite level, or will it not be able to? Will it be able to keep the hydronium concentration relatively level? No. Because there's not enough base form to react with the excess acid to get rid of that excess H3O plus, because there's so little of it, right? Small. Okay, so that's why we can't just have a weak acid be a buffer, okay? A weak acid could protect against added NaOH, but it cannot protect against added hydronium ion, added acid, okay? So now what we're going to do is, to solve this problem, we're going to add some sodium acetate. Why are we adding sodium acetate? Because what did we run out of? Acetate. So we can add the salt of the conjugate base. So added H plus will have enough base to react with. And if you are joining us on this recording because you were away or you're wanting to watch it again, if you go to, what is it, 5.5a, there's actually a list of buffer videos. And I probably have last year's lesson or the year before's lesson where I didn't forget to record the beginning part of the lesson. So there we are. Okay. And also, Mr. Colger walks you through this as well. So if you're like, Miss Spence, your videos take too long, Mr. Colger tends to do them in like nice little 7 to 9 minute chunks. So those can be quite lovely if you can put up with Mr. Colger's boring voice. But he puts out really good content. I should not make fun. Okay. What's that? Tyler does not do anything for us in Chem 12 until electrochem, and then he's back. So for our last unit, we get Tyler back, right? Yeah. Yeah. Okay. So when we add this sodium acetate, the concentration of acetate goes up. So this will actually, this goes up when we add NaCH3COO. So it's going to shift to the left. Now remember that CH3COOH started at 1.0 molar. So now that we have shifted left, the concentration is now a little bit more than 1.0 molar, because we've shifted left with the addition of the base. Because we have shifted left, what has happened to our hydronium ion concentration? It was pretty low, and now it's even lower. And because we have shifted left, we started with 1.0 molar, and now it's a little less than 1.0 molar. Is good? Okay. So now the solution has both. That was supposed to be highlighting, not scribbling out. That did not work very well. Now the solution has both a high concentration of the weak acid, and a high concentration of the weak base. So here is the summary. We have a high concentration of the acid, we have a high concentration of the base, and we have a very low concentration of H3O+. Will this new equilibrium be effective in bringing H3O+ back to close to its original level if we add NaOH? Yes. Are we good with that? Because it was good before. We had some of the acetic acid. The acetic acid allows this to shift to the right to produce more H3O+ to replace that which was lost. Now, what if we add some HCl? Can we now, if this increases, can we shift to the left? Yeah, because we've got lots of this, so we can shift to the left. So the answer is yes. I want to improve this sheet so we have some more stuff in here, but that's okay. Since the solution is now able to resist a change in pH upon the addition of a small amount of strong acid and upon the addition of a small amount of strong base, it is now a buffer solution, because of course a buffer has to be able to do both. But wait, this is something people often think. They think, we just mixed an acid and a base together. Don't they just neutralize one another? And the answer is no. The actual process of neutralization, where one rips something off the other and it turns all into, water and the salt, that requires a strong acid or a strong base. When you mix a weak acid and a weak base, they just hang out in equilibrium with each other. Nobody's ripping off protons. No one's donating protons. It's pretty they're just chilling. They're just hanging out and chilling. Okay? Okay. So let's go through this example here. Let's assume we have a buffer system, which means that we have a high concentration of the acetic acid, and we have a high concentration of CH3COO minus. Please go through and try and fill in. If we add some HCl, what is the stress? What is the shift? And what is the overall change in hydronium and the overall change in pH? And then you're going to do the same thing when you add NaOH. So please give that one a try. Once you are finished, I'd like you to check with your partner. Yeah, they're high. Yeah, and we're assuming we add a small amount of HCl to our high concentration and a small amount of the NaOH. No buffer system can buffer forever. If you threw in a liter of HCl, it would just overwhelm the buffer. Yes. What is the overall, when we're dealing with the addition of HCl, what is the overall change in H plus? It is an overall increase. It is a slight increase, yes? Because it increases, the system shifts, where does it come back down to? Slightly above. So it has increased, but not by a lot. So we can say a slight increase. And what has happened to the pH? If hydronium goes up, pH goes down. So we have a slight decrease. Similarly, when we've added some NaOH, what has happened to the overall H3O plus concentration? It will have a slight decrease. Because remember, if here's our initial H3O plus, we add some sodium hydroxide and it drops, but then the system shifts until what? I'm doing like this little drama up here, and none of you are paying attention. Well, a few of you are. Okay, so we have hydronium, we add some NaOH, so the hydronium concentration drops, and now the system shifts until where does the hydronium end up? Slightly below the original concentration. Okay. So there is a slight decrease in H3O plus, which means what happens to the pH? Slight increase. Yeah. Is it important to say this slide? I think so, yes. Because that's the whole point of a buffer, is that it's not a big increase, it's a little increase. Yeah. So what we're going to do now is that we're going to take a look at a little graph of what happens with this, because, I mean, me being up here doing my little, interpretive dance graph is not quite the same as having one in your book for you. So here we go. Right here, this is our concentration of H3O plus. And this is in a buffer system. Okay, and then we add some HCl, the hydronium ion concentration goes up. And then the system shifts to the left. Here's our system. Actually, I'm going to even leave out the water this time and just have H plus and CH3 COO minus. So this increases, this shifts to the left, and as it shifts to the left, the hydronium or hydrogen ion concentration goes back down. However, we end up with a small net increase. Okay, so that's what it would look like on a graph. And if we have a net increase in H3O plus, we have a small net what in pH? Decrease. So now what I would like you to do is I would like you to draw a graph of pH versus time when the small amount of hydrogen chloride is added to the buffer. So now instead of doing hydronium, you are going to be drawing in pH versus time. Okay? So you've got pH on that axis, give that a go. All righty? Huh? I don't know. I was planning on doing something. Let's just, okay, yeah. Something's crazy. Actually, if we assume that the concentration of the CH3 COO minus is approximately equal to the concentration of the CH3 COOH, at least initially, what would be the initial pH of the solution? Because I was going to label it pH 7, but then I realized it wasn't 7. You went down the same road I did. Yes. Ho, ho, ho. If these two are equal, where are we? We are at the half equivalence point. What is true at the half equivalence point? First of all, these two are approximate or equal, but at the half equivalence point, what else is true? Ka is equal to the concentration of hydrogen, and we just put a half there to indicate that that's at the half equivalence point. Okay? So what would our pH be? pH would be what? pKa. Now, is anyone puzzled by where this came from? Would like a little refresher on that? Anyone? Okay. All right. If you're too embarrassed to ask, you can always come ask me later. Okay, when HCl is added, what happens to our pH? It decreases. And then as the system shifts, it goes back up, but it ends slightly below. Yes? Okay. Are we good? Yeah. Carrying on. All right. Now we're going to use the same buffer solution. We have high concentration of the CH3COOH. We have a high concentration of the conjugate base form, and we add a small amount of NaOH. What happens to the equilibrium? Yes. It shifts to the right because the hydronium neutralizes with the hydroxide, and then it will shift to the right to bring the hydronium back up. So if you see, here's our graph. We added some NaOH. As the equilibrium shifts right, the H3O plus increases, but it does not quite get it back up to where it was. So we'd have a slight net decrease in H3O plus, okay? Which would mean a slight net in pH. If we have a slight net decrease in H3O plus, we have a slight net increase. And you can say thank you to Mr. Colger for these lovely diagrams because I just stole them from him. Could you draw a graph of pH versus time when we add a small amount of NaOH to the buffer? I'm hoping your graph looks something like this. Is that correct? It does. Good. All right. I think this, honestly, this is just more rambling about the same thing. Like, what if we only had the weak acid? If we only had the weak acid, would it be able to buffer effectively? No, because it can buffer against, because it's an acid, it can buffer against base. But if you don't have the base form, you can't buffer against acid addition, okay? So we're not going to fill all that in, but we will look at the key point is that a buffer system must have relatively large, and everyone always wants me to qualify exactly what relatively large is. I think 1 decimal place, like I think 0.5 would still qualify, but I don't know. I mean, honestly, whether it's an effective buffer depends on how much acid you are adding to it, right? So you might be able to make an effective buffer out of 0.1 and 0.1, but you'd definitely be safe making it out of 0.5 molar, 0.5 molar, or 1 molar, 1 molar. Yes? Okay. And don't worry, you'll be asked questions like, which of these is the most effective buffer? And you'll be given one where the concentrations are smaller, and you'll say, no, it's not that one. And you'll be given one where the concentrations are bigger, and you will say, yes, it is that one. So you won't be asked to decide like, oh, is 0.5 big enough? Do I know? Can I? Not unless you're given some actual numbers of the amount of base you're adding. If the moles of base exceed the moles of the acid in the buffer, then it would not be effective, right? So if you can overwhelm the buffer, you might have to do some calculations, but I've never seen it on AP. You will not have to do any buffer calculations on the regular test, okay? There is a 5.5C, which is buffer calculations. I've not yet finished it. The answer key is still being made. So it will slot, and because it's not part of the regular one, I thought it would be nice to have it in a separate thing. So when you're studying for your exam, you can be like, oh, I don't need to do buffer calculations for the regular exam. Is good? Okay. Okay, so anyway, the key point is that maybe 0.5 is a good sort of cutoff point for what's relatively large. I can't say for sure. You need to have a relatively large concentration of both the weak acid and the conjugate base. Which means in this system, you need lots of CH3COOH and you need lots of CH3COO-. Can you go into the back room there and grab me a bottle of acetate ions? Like, will you see a bottle back there labeled acetate? No. Why not? Yes. It's not possible to have isolated ions. If you have an anion, you must always have a cation. Are you guys okay with WO for without? Okay. So, no, you cannot. They must always be paired with a cation. Could you guess who is a good cation to pick? Sodium. Right? Just like when we were doing the solubility stuff, who are you going to pair it with? You're going to pair it with sodium because there's lots of sodium around. It's really common. It doesn't react with anything. It's soluble with everything. You could also choose K if you want to, but why bother thinking when you could just choose sodium? You know what I mean? Don't choose iron. Why would you not want to choose iron? Yes? Iron is not very soluble, but also it hydrolyzes, which would be very problematic. Yes? Okay. So buffers are either mixtures of a weak acid plus the salt of the conjugate base. So that's why we have to have the salt, the NaCH3COO. So the salt of the conjugate base. Or you can have a weak base and the salt of its conjugate acid. And they have to be in relatively large concentrations. Oh, look, I did go for it. I said relatively large should be greater than or equal to 0.1 molar. I put down a number. I'm not sure if that's correct or not, to be honest, but just go with it. We also usually try to have the concentrations be approximately equal. So, generally, if you want an acidic buffer, one that buffers at pH less than 7, you will use a weak acid and the salt of its conjugate, whoops, base. So for example, if we had HCN as our acid, what would we want? And it was at 0.5 molar. Oh, pen died. Let's see if we can fix that. If the HCN concentration was approximately 0.5 molar, what would we probably want NaCN concentration to be? Approximately 0.5 molar. Okay, you want them to be similar. Could you please write the equation for the equilibrium formed by this buffer system? Is good? Technically, you could also write it. Is there another way you could write it? I mean, you could write it without the H2O. Okay, but I'm talking something in addition, like beyond that. Is there another way we could write a buffer system that contains HCN and CN minus? Pardon me? With OH, and so who would be in the reactants at that point? CN minus plus H2O in equilibrium with HCN plus OH minus. But it's because we're always working in pH, it's usually easier to use the hydrogen form. Yeah? And yes, always get rid of your spectator ions. You don't want sodium kicking around, cluttering up your equation, making it confusing and complicated. Okay?
Oh, very good.
Now, I got a question for you. Actually, before we carry on here, let's go to our data pages and look at these guys here. If you had an approximately equimolar mixture of let's just say HiO3 and IO3 minus, at approximately what pH would that be buffered if you had an equimolar, 1.0 molar of that and 1.0 molar of the other one? At approximately what pH would we be buffering? Would it be a high pH or would it be a low pH? It's going to be a low pH because what would the hydrogen ion concentration be at which we are buffering? So we would be buffering at concentration of hydrogen is equal to, guess what? Because if you remember, when the concentration of HiO3 is equal to the concentration of IO3 minus, what else is true? Concentration of H plus, this is our half equivalence point, is equal to Ka. And that's what we've done here. Yes? So if I said to you, could you please go pick me out an acid that would buffer at, let's see where a good one is. Ooh, could you pick me out an acid that would buffer at pH 7? Tell your partner, see if they agree. Okay, do I go with Nathan or Elliot? What do you guys think? Oh. Oh. I think I should ask somebody else entirely. Someone else have an answer for me? Alvin. HSO3 minus is an excellent choice. Now, we would have to combine it with who? We would have to combine it with SO3, 2 minus. And so really the compounds we would be using would be NaHSO3 and Na2SO3. Yeah? Okay. This kind of thing where you're like, what would be a good choice for the buffer? That's not on the regular exam, okay, on our regular testing class, okay? It could be, honestly, I don't know. I'm going to go through and pick out a bunch of buffer questions from the old AP exams and kind of scout and see what's in there, typically. Can we have, is it possible to have an acid and its conjugate base that buffer at pH above 7? Could you please pick an acid, tell your partner about it. I don't want to hear from Elliot or Nathan. Please pick an acid that buffers, acid with its conjugate base that would buffer at pH above 7 if we used an equimolar mixture.
I'm really water.
Water will not buffer. Water just says, oh, look, hydronium, here it is. Stay around. Are you answering the question? You're asking a question. I will take an asking question. Shh. I did not understand that question. Could you run that by me again? No, there were just too many pieces and I lost one of them somewhere. Yeah. Yeah, 10-ish, right? Yeah. And you can actually play a little bit with the ratio of the base and acids to hone in on exactly where you want that pH. We'll look at that later. Okay? Yeah. It'll be close to that, but you can play around with it within that little range. So which of these acids could you use along with its conjugate base to buffer at pH greater than 7? Which ones could you use? Alvin. You could use ammonia And ammonia, absolutely you could. And in that case, you'd be using a weak base. And what would the salt of the conjugate acid be? What could you choose? NH4, NO3. Yes. Because you can't make a salt of NH3. NH3 is a neutral compound all on its own. Could you use phenol? Would phenol work? Yes, because the Ka is less than 10 to the negative 7. In fact, you could use any of these acids. Could I use, oh, now what if I wanted to buffer at pH less than 7? I could use any of pH less than 7. I could use the aluminum one. Why is it not writing? There we go. Okay, try that again. There we go. Is there another one we could use to buffer at pH less than 7? Yeah, you can be like, okay, I could use any of these to buffer at pH less than 7. Where do I stop? Do I stop yet? Buffering pH less than 7? And do you understand why we're buffering at pH less than 7? It's because the Ka would give you a pH less than 7, like it would give you a pH of 5-ish. These would give you a pH of 4-ish. This would give you a pH of 3-ish. These would give you a pH of 2-ish. Where do I need to stop, though? Can I go up into my strong acids and bases? Why not? Why can't I use a strong acid and its conjugate base? It's not an equilibrium. Like, you cannot go this way. It would be like, okay, great. I can absorb lots of hydroxide, but I can absorb absolutely no hydrogen ion. So it has to be a weak base and its conjugate acid, so you get that lovely equilibrium. Okay. Yes. Why does hydronium work as a buffer? It doesn't. It's part of a buffer system, but it's not like the acid with its conjugate base. Having hydronium and water, its conjugate base will not produce a buffer. Okay, because that's just like having acidic solution. Yeah? Yeah. Now, what I'm telling you here is the falsehood that we tell the regular chemistry 12 students, which is if you want a buffer at pH less than 7, you choose a weak acid and the salt of its conjugate base. But as you know, about at least a third of them will buffer at a pH above 7. Yes? These ones down here will buffer at a pH above 7. Weak acid conjugate base. But for regular Chem 12, we just say, if you take a weak acid and a salt of its conjugate base, you will get an acidic buffer. It will buffer pH less than 7. Because we're not mucking about with calculations. Honestly, Chem 12 buffers are like, buffers, moving on. Right? Like it's seriously, it's very, and I actually find it becomes confusing because you don't really understand it. It's like, buffers, moving on. So I will put in things in the, like, I'm going to make sure I don't put in things in the test that contradict the actual knowledge. Do you know what I mean? Like, yes, you could use HCN. And you could buffer at a pH of 10-ish, okay? Okay, now again, if you want a basic buffer, this is again Chem 12 lore. We'll call it lore. Because is it true that every time you have a base, if you have a weak base, and the salt of its conjugate acid, that you will buffer at above pH 7? The chances are, yes, it's most likely the case, but it would depend upon the KB, right? Okay. For AP, we'll go into the math more and see how we can actually make a basic buffer from a weak acid and salt of its conjugate base and vice versa. But for most purposes, the general rule is acidic buffer, use a weak acid and the salt of its conjugate base. Basic buffer, use a weak base and the salt of its conjugate acid. Okay? Generally. Buffer capacity. No matter how high. Okay, no matter how high you make the concentrations of the weak acid and the weak base, at some point for any buffer system, you can add enough H and OH to overwhelm that buffer. You will use up one or the other of the weak acid and the weak base. This is known as the capacity of the buffer, or the limit of the buffer, and it is determined by how much acid you have and how much base you have. So in other words, the capacity is determined by the number of moles of weak acid and by the number of moles of weak base. The higher the number of moles, the higher the capacity. The lower the number of moles, the lower the capacity. Yes? Okay, cool. That was awesome. So you might get a question like this one: of the following 1 liter solutions, which has the greatest buffering capacity? The one that's the biggest. Yes? Because you have more stuff, you will run out less soon. You will run out later. Later was the word I was looking for. Whoa, less soon. Do you know who has really good words for words? Is Ms. Neiman. Ms. Neiman is always calling things that she's always making up words for other words that are not the thing. I'm trying to think of. I can't think of any offhand, but they are really good. They're really fun. Okay. Okay, so let's say we have, oh look, I have a high concentration. That's high, yes? Remember I said 0.1 is high? Okay. So we have a high concentration of CH3COOH. We have a high concentration of CH3COO minus. But now let's say we add 1.5 molar. 1.5 moles of HCl to 1 liter. What will happen? We add 1.5 moles to 1 liter of this solution. Does it become a little bit more acidic? Or does it become lots more acidic? Lots more acidic, because once we've added 1.5 moles, we are going to have 0.5 moles of HCl will be in excess, yes? Because in 1 liter, we would have 1 mole of CH3 COO minus. So we could buffer 1 mole, but that other 0.5 moles, it's just like, whoa, 0.5 moles of H. Now we have it. This is more than the acetate can handle. React with. Okay. Blah, 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 blah. Key point, a buffer system cannot be made from a strong acid and the salt of its conjugate base, nor a strong base and the salt of its conjugate acid. We all already talked about that. What else do we have? Oh. AP. Actually, let's do this. Because this requires you to make thinking things, thoughts, thinking things, thoughts. What chemical could you add to 1 molar hydrofluoric acid, HF, to prepare a buffer solution? What chemical could you add to HF to prepare a buffer solution? Alvin. NAF. To a final concentration of about 1 molar. There is something else that you could add to this solution and end up with a buffer. I want you to think about it. Shush, shush, shush. We could add potassium fluoride. We're not going to add potassium fluoride. Think about it, think about it, think about it, think about it. Let everybody think about it. Francium fluoride. There we go. Something that will not create a radioactive buffer. Something that does not contain fluoride. Bam! We could add some OH. How would we get OH? It would be in the form of sodium hydroxide, because do you remember what happens? If you add sodium hydroxide to HF, you'll neutralize maybe half of it, right? And now you have half of the acid is unneutralized and half of it has been converted to its conjugate base. So you'll have about 0.5 molar of each. Is good? That will definitely not come up in regular chem, and it might not come up in AP. I have seen it once in AP. Yes. Okay, so we could add answer 2. We have how does this work? Isn't that fortunate? Okay. Let's look at the reaction between HF and NaOH. So if we start adding NaOH, oh, look, we have a Ricfa table, okay? So if we start off with 1 molar HF, and we add sodium hydroxide until it is at half of that concentration, this will neutralize half of the acid. Okay, so how much acid are we left with at the end? We started with 1 molar, now we only have 0.5 molar. What happened to the other 0.5 molar? It got turned into NaF. So now we have 0.5 molar NaF. And if we have 0.5 molar HF and 0.5 molar NaF, what do we have? We have a, what's the whole lesson been about? Buffer. We have a buffer, okay? Okie dokie dokie dokie. All right. Alvin, did that make sense? Cool. I'm growing to love the Rictva table. I am. Oh, we got 5 minutes left. Why don't we answer this last question here? What the heck? Might as well push through. To a large concentration, so this is your alternate way to perform a buffer. This is AP only. To a large concentration of weak acid, what will you add? A strong base. Enough in order to neutralize how much? Half, about half the acid. You're going to end up with the weak acid and the salt of its conjugate base. That will be the result. Or if you're looking at working with a weak base, to a large concentration of a weak base, you can add enough strong acid to neutralize half the base, which will result in a mixture of the weak base and the salt of its conjugate acid. Could you please tell me what salt, this is method one, this is the regular chem one, what salt could we add to NH3 to make a buffer? Why are you guys all like so opposed to talking, like answering questions? Why? There's like 4 or 5 of you in here who answer questions on the regular, and then nobody else answers anything. Daniel. NH4NO3 will do very nicely. And actually, to be honest with you, because we're not dealing with anything else, like NH4Cl would also work quite well. Cl is not, it's soluble with most things. So unless you're working with silver or lead or mercury, you're probably in good shape, okay? Approximately what concentration would you want the salt to be in the buffer solution? 1 molar. Write the equilibrium system for this buffer. Would this buffer solution be best at buffering above or below pH 7? Above pH 7. You could check with the Kb, right, of NH3, or the Ka of NH4+. What other type of chemical, not a salt, we're not leaving yet, what other type of chemical, not a salt, could be added to the NH3 to make a buffer? A strong what? Acid. Give an example of such a chemical. HCl. And I will leave you on your own to explain how the addition of this chemical can produce a buffer solution, show the relevant reactions. Your homework, Do numbers 1, 2, and 3 on page 85.